Alright, so for section 2, now we're giving what we did in section 1 kind of a name. So now we're going to be dealing with definite integrals as well as Riemann sums. So what is a Riemann sum? It's the process that uses sigma notation and a limiting process to consider infinitely small widths or change of x values to get a more accurate approximation of the area under a curve. It's exactly what we were doing, but the idea of Riemann sum is just taking all those areas and taking the limit as that change of x approaches 0, or as those partitions approach 0. So saying that eventually those rectangles will be so tiny that it will be an exact approximation. LRAM, MRAM, and RRAM are examples of a Riemann sum. So let's consider the following function and the area under the curve from A to B using MRAM. So using MRAM, of course, it means that in between each subinterval, and I've already broken this up into the subintervals, here's A to B, and I've broken this up into 5 subintervals. And since we're doing MRAM, in between each interval, I'm going to go to the center, and I'm going to call that C1. I'm going to go up on C1, and then I'm going to make my rectangle for those 2 subintervals. Okay, I'm going to do the same thing for C2. Here's the midpoint, and now I'm going to make my rectangle for these 2 subintervals. Here's C3, up to the point, make my rectangle. C4, up to the point, make my rectangle. C5, up to the point, make my rectangle. So basically here we can see that this is going to be area 1, this is going to be area 2, area 3, area 4, and area 5. So the idea is that the Riemann sum is going to equal the sum from I equals 1 to n of the function f of ci times change of x I, depending where I has begun. Okay, so if we remember from the definition that I gave you guys last week, one second. Nope, we forgot one part, right? Because I said that this now, Riemann sum, we are taking the limit as the partitions, we're going to call it, it's like a P with double lines, approaches 0. And then you take the sum. And the partitions is the same thing as saying change of x approaches 0. So it's as this partition gets smaller and smaller and smaller and smaller, so that you have a very, very small width. Now, it's important to remember the similarities between Riemann sum and the definite integral. So, in this case, we know that this is how Riemann sum is written. And the area under the curve for a definite integral, or you know what, I'll write it in just a sec. But let's remember this. We're going to come back and fill this out. Okay? And remember, in Riemann sum, this is representing each individual width. Okay? Alright, the norm of the partitions. is represented by P. Basically, what this is saying is that the longest subinterval find the exact definition. It's the longest subinterval to tend to 0. All right, so we have been using the same subinterval, but it's not always going to happen. But we are going to be using the same subinterval, okay, for the most part. So just remember that change of x from now on and p basically mean the same thing. This is the partition, and change of x is also the partition where we are taking our slices. Okay? Okay, using smaller and smaller change of x to get more rectangles, eventually we get the limit produced by letting change of x approach 0, or the other way of saying this, the partition is approaching 0. And remember, this is the norm of the partition. That's what this definition is. So that's the idea of Riemann sum. All right, the definite integral. How do we find the definite integral? So first, we find the areas using f of ci times the change in xi. Then you add up the areas, which is exactly what we were doing in section 1. So that means you take the sum of from I equals 1 to n of f of ci times change in xi. Now, one more step for the Riemann sum is you take the limit which is the limit as change of x approaches 0 of the sum from I1 to n of f of ci times change of xi. And now this and step 4, which is the definite integral, are equal. So the definite integral from a to b, okay, for our subsection of f of x dx. So we need to look how these two are related. But before we do that, let's look at the terminology of this thing. So here's the idea. You have the integral sign. So this is the integral sign, which means let the width go to 0 and add up the area. That's basically what the integral sign means. It means let the width go to 0, then add up the area. That's basically what we're doing when we take the integral of something. We're trying to let the width of those partitions eventually equal 0. And then of course you have a section, a big section that you're dealing with. And then this is the lower limit. This is the upper limit. And then you have your f of x, which is called the integrand, which aka is the height of the area that you are going to be taking. And then times dx. And dx is important to remember that it is the width, aka change of x. Now, it's dx here. X is our variable of the integration because that's what we use. But remember, if we are going to be using f of t, then this is just going to be d of t. If this is f of u, this is du. If this is f of s, this is ds. So what you put down as the letter right here depends on the actual function. Okay, so x is going to be the variable of integration. So what this is saying is the integral of f from a to b. And when you find the value of the integral, you have evaluated the integral. Okay? So let's look at this example. This is what I was telling you a little bit ago. We have to be able to represent the Riemann sum as a definite integral. Okay? So basically what we are doing right now is we have been given the Riemann sum, which is right here, and we have to rewrite it as a definite integral. Okay? So first off, it is going to be a definite integral, so there we go. There's my definite integral. Now, my partition, or my area that I'm working with, is from 0 to 1. So my lower limit is 0, my upper limit is 1. Okay? And then my function is basically right here. So my function is 2, and here it's going to be ck, and remember, where did we write down ck? These are the subintervals chosen for the partition. This is the expression for the Riemann sum, so how many partition points did we have? This is going to be represented by 2x cubed. So basically the idea is our ck's are going to be our x variables. But remember, this is the dummy variable. We're just using it right now. You could use mt, it doesn't really matter. And then our change of x, if you remember right here, what did I say? Our change of x, the width in the integral, is represented by dx. So change of x is just going to be dx. And there we go. This is us expressing the Riemann sum, the limit of this weird looking function, as a definite integral from 0 to 1. Okay? All right, definite integral and area. So, rules for curves that lie partially above and partially below the x-axis. You're still going to be doing the same exact thing. You're always going to draw rectangles between curves and the x-axis. But the difference is that you're going to treat the areas above as a positive value, positive integral, and you're going to treat the areas below as a negative value. So in this case, if we wanted, let's do a mid, an MRAM. Okay. So here's my MRAM. So there's my M. Now, you see how I'm drawing in between the curve and the x-axis, okay? So these two got drawn on the bottom. Now this one is going to go up to the curve, and I'm going to draw my rectangle right there. So here we go, mid, go up to the curve, draw my rectangle, mid, go up to the curve, draw my rectangle, midpoint, go down to the curve here, draw my midpoint, draw my rectangle, midpoint, go down to the curve, draw my rectangle, and midpoint, go down to the curve, draw my rectangle. So if I label these as A1, A2, A3, A4, A5, A6, A7, A8. So which ones are areas above? They're going to be my A3, A4, and A5. And then the ones below are A1, A2, A6, A7, and A8. Alright, and we'll do some examples of these in class and how you are going to be adding up the different integrals. Alright, the constant function. If f of x is c from a to b, so here's my constant function right here, f of x is c, where c is constant value, then basically what we know, and we've already kind of talked about this before, but we're going to show a proof, we know that the area is equal to length times width. So my length right here is going to be represented by f of x, f of a, which is c, right? So my length is how high, and this thing is, the height is c. Now my width is b minus a, right? You subtract the b minus a and you figure out how wide this is. So this is the geometry. Basically, this gives us a proof that says that anytime you have a function from a to b, f of x dx, where the function a to b is constant dx, then basically the integral is just going to be c times b minus a. And why is that? So let's take this part right here and actually integrate it. Let's show the proof. Now remember, an integral of a constant, you just add an x. So there's the integral of the constant, and then it's from upper limit b, lower limit a. So now we take c times input the upper limit minus c times the lower limit, and then this gives us c times b minus a. And that is our area. So whenever you have a constant function, all you have to do is really multiply length times width. So let's look at this example. So here's our constant function. Basically the idea is if you take the integral, so what is the integral of 4? The integral of 4 is going to be 4x from 6 to 3. So let's evaluate this. This is 4 times 6 minus 4 times 3. And that gives us 24 minus 12, which is 12. Okay, so this is actually evaluating it. Now what we could have done using the proof is, because that's constant, it's just going to be 4 times b minus a, right? It's going to be c, times b minus a, which is 4 times 6 minus 3, and that's 12. So of course both are correct, but one is easier if you spot it. Okay. All right, last page for today's notes. So this is not that bad, but if for linear functions, if f of x is linear, then and the function is continuous on a to b, then we have to do a little bit of something, because if I wanted to figure out what the area of the curve was from here to here, I'd have to take my partitions a little bit simpler. Instead of using rectangles, what I could do is separate this into here's area 1 and here's area 2. And the only reason I can do that is because we know that this is going to be a perfect triangle. So geometrically, I know that I can figure out the area of y equals x if I have my triangle. Okay? So the proof for A1 is, of course, it's a rectangle. So A1 is going to be length times width, right? Which is equal to height A times B minus A. And that ends up giving us if I distributed AB minus A squared. We'll see why this is important in just a sec. Now, for A2, for this part right here, for my rectangle, it's going to be half of the base times the height, right? And basically what this is saying is it's half. Our base is still B times A. And now our height, oops, I should have put my B like a little bit higher over here. So my height is also B times A. Okay, so here's A and here's B. So now when we simplify this, we end up with 1/2 B squared minus AB plus 1/2 A squared. Basically what I just did is I FOILed and then I distributed the 1/2. So now if I add the two together, the area total, which is A1 plus A2, you get, let's add this and this, okay? You end up with, I'm not going to show every single step, you guys can do that on the side, 1/2 of B squared minus A squared. And we'll do an example where we're going to use this type of partition. Okay, and let's do an example without a graph. So here is the function. Change that 4 to an x. It should have been an x. So first let's find the integral of x, which ends up being x squared over 2 from 6 to 3. So the idea is 6 squared over 2 minus 3 squared over 2. Simplify, 36 over 2 minus 9 over 2. And you end up with 27 over 2. Okay, and the idea is that if you did this just like before, you're going to get the same exact thing. So B is our upper limit minus our lower limit divided by 2. So 6 squared is 36 minus 3 squared, which is 9, divided by 2 is the same exact number. Okay, so these are just easier ways, but the thing is you can still figure them out with the integral. So it's up to you if you want to memorize it that way or not. Alright, the shortcut for evaluating a definite integral with a function is a polynomial, and we've done this a million times. So for each term of the polynomial, raise the power, So this is how you find the antiderivative. You raise the power of each term by 1, and then divide each term by the highest power. So let's look at this example. So this, we're going to raise the power by 1. So right now it's 1. So I'm going to raise it to 2, and I'm going to divide that by that power, by the high power that I just got. Plus 4, let's raise the power by 1. So right now the power is 0. It's going to be raised to x. And we're going to take it from upper limit 2 to the bottom negative 1. So let's plug in. So this is negative 2 squared over 2 plus 4 times 2 minus, very important to put this parenthesis over here because you are going to be subtracting multiple terms, and then negative 1 squared over 2 plus 4 times negative 1. So do the math. 2 squared is 4 times negative, which is negative 4 divided by 2, that's negative 2 plus 8 minus, and you notice how I'm placing the parentheses correctly. So negative 1 squared is 1 times negative 1 is negative 1/2. 4 times negative 1 is negative 4. Okay, keep going. So negative 2 plus 8, which is 6 minus negative 1/2 minus 4, which gives us negative 9/2. So you finish this off and you end up with 21 over 2. Alright, that's it for today. I know this was long, but you guys can probably make me go a little faster on YouTube. We'll do the next part, calculating indefinite integrals on the calculator, and is actually the way to do the RRAM and MRAM and LRAM on the calculator as well. We'll do that together, probably not tomorrow, but in the next 2 days. Okay? Alright, enjoy.